Swayam Prabha. Digital India. Educated India.
Welcome to this course on transition metal organometallics in catalysis and biology. We have been discussing various aspects of olefin metathesis in the past few lectures, starting with its origin. Then we have looked into the developmental aspect of the metathesis reaction with time, like how the reaction evolved. We have also looked at the mechanism that was developed in order to understand this metathesis reaction. We have also noted and observed in the previous lecture that how understanding this mechanism was a important breakthrough, because as that led to unification of several group of reactions which fell within the umbrella of larger group of metathesis reaction, and about 15 variant of about 8 variant of olefin metathesis reactions all came into being, and all came under the umbrella of olefin metathesis. Even on the alkyne metathesis front, we saw that alkyne metathesis also drew its parallel from olefin metathesis, and about 5 variants of alkyne metathesis were also reported subsequently. We had seen this development from various angles, from various perspectives, in order to get a holistic understanding of this phenomenon of olefin metathesis, which indeed is a very important development and has rightfully been recognized with the award of Nobel Prize in 2005. So, today we are going to add a different perspective to our discussion on olefin metathesis, and this more or less is about the catalyst development aspects. Now, so far we had noted that metal carbenes are important active catalyst for olefin metathesis. So, these are called carbene species as important catalyst for this olefin metathesis reaction. And there has been a subsequent studies on synthesis of various kinds of carbenes, and as a organometallic chemist, this metal has been studied for studied as a function of metal, with several metals coming into play, for example, tungsten, molybdenum, ruthenium, so on and so forth. So, as a result, many carbene complexes were subsequently synthesized, starting with the Fischer carbene as well as Schrock carbene, tantalum like early transition metal, so on and so forth. And these also led to formation of various types of metal carbene species, Fischer type carbene and Schrock type carbene, and where we have also discussed this in great details, and where we had observed that even though these all are metal carbene moieties, however, their reactivity as well as the electronic nature of bonding between metal and carbonic fragments are different, and hence they behave differently. In this context, today we are going to focus our discussion bit more on metal and trying to understand the function of the reactivity of the metal carbene species as a function of metal. Now, what emerges from the various synthetic studies that have been undertaken is the fact that molybdenum catalysts are very reactive, are usually more reactive in metathesis reaction. On the other hand, ruthenium catalysts are easy to handle. So, this sort of implies that ruthenium complexes or catalysts are more moderate in reactivity, and hence they do not decompose or sometimes they are more stable in aerobic conditions, and because of which the ruthenium catalyst becomes easy to handle. The subsequent observation are the ruthenium catalyst with NHC ligands are most active. Now, this is an important observation and also an important breakthrough, because that gave a lot of importance to the developmental aspects of NHCs as a ligand. Now, in our last class we have also spoken about how these singlet carbenes in the form of N heterocyclic carbenes which are of the formulation of this type have been synthesized and stabilized by Ardengo, and that what we see later, that becomes a very good ligands for developing these metathesis catalysis. So, this is an interesting development which sort of came out of different carbenic complexes that people have gone on to make in order to study the stabilization of metal carbene moiety, and also the implication of carbene complexes in olefin metathesis reaction. Finally, an important development is in synthesizing chiral catalyst in for asymmetric olefin metathesis reaction. So, this also is the next level of development where one can carry out or one strives to undertake this metathesis reaction in the next level in terms of being able to doing it in a asymmetric fashion using chiral catalyst. So, all of these led to development of the catalyst from different aspects in terms of their reactivity, in terms of their ability to being ability to being handled in air as well as in their ability to carry out the reaction in asymmetric fashion, and also the rate of the reaction. So, among the various metals that have been used for studying for making these carbene complexes for studying metathesis reaction, the one that emerges out successfully is this ruthenium catalyst, because this is what made the carbene complexes carry out metathesis reaction under aerobic conditions in high yield. So, ruthenium emerge out to be the victorious in this race for developing catalyst for carrying out olefin metathesis reaction. So, it is ruthenium winning in the end, because it sort of brought the whole carbene chemistry, which is extremely air and moisture sensitive, out of glove box to be able to carry out this reaction in open bench under aerobic condition, which added a great amount of practical utility to the reaction, and hence making the reaction so popular in the world of organic synthesis. So, we are going to talk a bit more about the advantages of ruthenium catalyst in olefin metathesis. And what we see that this ruthenium forms easily stable carbene complexes. The ruthenium carbene complexes are also air and moisture stable. Third, the another important attribute of ruthenium catalyst is this ruthenium carbene complexes are tolerant to a wide variety of functional group, that they do not react and get poisoned by the functional group. And what is the outcome of this is that it does not it does not sort of participate in other kind of secondary reactions or decomposition reactions, and hence overall these ruthenium carbene complexes for metathesis reaction. So, this is the overall verdict in favor of ruthenium winning over, and this probably is what made Grubbs famous, because Grubbs is the one who developed ruthenium carbene catalyst for metathesis reaction. And it is to be noted at this juncture is that Grubbs initial proposal or hypothesis for the mechanism of metathesis reaction did not turn out to be true. However, that is made up by this development of ruthenium catalyst, which sort of brought these very air sensitive metal carbene complexes out of the glove box for in open air for benchtop chemistry, which added great applicability to this reaction. Eventually Grubbs went on to win Nobel Prize because of this contribution. So, it is Grubbs who is noted for the development of ruthenium catalyst for metathesis reaction, and the reason they have become so successful is illustrated over here by the fact that they are very easily synthesizable. They are also very easy to handle, stable in air and moisture, and also they are tolerant to wide variety of functional groups. So, a large types of different reaction can be taken up using ruthenium catalyst. So, with this we are going to now focus a bit more on Grubbs chemistry about the development of ruthenium carbene complexes. Particularly we are going to start off from its synthesis of how these complexes were synthesized. Ruthenium carbene catalyst. And it starts with RuCl2 PPH3 whole thrice, that when react with this diazo compound in dichloromethane at minus 78 degrees centigrade gave this ruthenium dichlorocarbene complex R equals methyl ethyl. Also this when treated with another para C6H4X again in dichloromethane at minus 78 degrees centigrade gave this ruthenium dichlorocarbene complex with further reacting with 2 cyclohexyl phosphine 2 equivalents in dichloromethane at 20 degrees centigrade giving PCY3 X equals hydrogen chloride. So, the point to note here that these are kind of very facile reactions which are synthesized from this ruthenium dichloride triphenyl phosphine trace compound by reaction with this diazo the diazo compound and that it gives rise to various carbonic complexes as is shown over here, here as well as here, and then he had also shown a reactivity of these carbon complexes in terms of removing this or replacing this triphenyl phosphine with more bulkier tricyclohexyl phosphine, and this is just done by reacting with tricycle 2 equivalents of tricyclohexyl phosphine in dichloromethane at 20 degrees centigrade. So, these shows that how easy it is to synthesize these ruthenium carbene complexes by the method which has been reported by Grubbs. The Grubbs also did the analogous experiment similar to what we had discussed about Fischer in the previous class that he took the ruthenium carbene complexes and reacted with various olefin to generate the subsequent new type of ruthenium carbene complexes of the olefinic fragment and different olefin, similar to what we had observed the Fischer did in the earlier discussion. So, we are going to discuss that in bit more detail. So, this is best illustrated by this ruthenium dichlorocarbene complex. So, that when treated with ethylene C2H4, then an olefin which is a fragment of C2H4 and this is eliminated along with a new ruthenium dichlorocarbene species, similarly the reaction with another olefin gave the corresponding different olefinic fragment along with a generation of a different kind of ruthenium R equals methyl ethyl the reaction with an alene eliminated the corresponding olefin with the generation of the following interesting carbene complex. And lastly, the reaction with another diene eliminated and gave this interesting ruthenium carbene complex. So, this is a very beautiful study in which one could show Grubbs had shown that how this ruthenium carbene moiety could be converted to 4 different types of 4 different types of ruthenium carbene compound depending on the reaction. So, this indeed is a very interesting result which had come out of this Grubbs study. Now, these compounds furthermore highlight the importance of ruthenium in metathesis reaction, because what it shows is the versatility of formation of various kind of ruthenium carbene complexes under reaction with different olefins, and this further reinstates the fact that these ruthenium carbene complexes can generate many other active species, carbene species, by reacting with different olefin during the course of the reaction, and this is what has been highlighted as the chain aspect, chain reactivity aspect of olefin metathesis reaction. So, with this we come to the end of today's lecture, where we have discussed about the importance of ruthenium in developing olefin metathesis catalyst. What it turns out that ruthenium by far is the best choice for developing olefin metathesis catalysis, particularly from the fact that these complexes are easy to synthesize, they are air and moisture stable, they are functional group tolerant, and they are the ones which can be used under aerobic conditions. So, it is ruthenium which has brought the whole of metathesis chemistry from the confines of rigorous handling dry box to the more amenable and easy to use benchtop chemistry. And this had been a seminal contribution of Grubbs, which indeed had made otherwise so difficult organometallic chemistry being so easy to be carried out in open air. So, we had looked into the reason as why ruthenium succeeded over other kind of carbenes like Schrock and Fischer carbenes in developing olefin metathesis reaction. We have also looked at the versatility of the ruthenium carbene complexes in terms of the one type of ruthenium carbene complexes getting converted to other type of ruthenium carbene complexes as a course by the treatment with different olefins. So, with this we again come to the conclusion of today's class, and we are going to be looking into the catalyst development aspect of olefin metathesis reaction in much more detail when we convene for the next class. Till then, goodbye and thank you.